Kaku once commented that we will need to rework our course books on the start of the universe. Everybody has been enthusiastically anticipating a specific picture, which has now been made public. This picture from the James Webb Telescope uncovers strange cycles in the universe that challenge our logical understanding. Since the send-off of the telescope, not only have our speculations on the universe's beginnings been tested, but indeed, even exoplanets have started to oppose our comprehension of physical science, totally flipping around our thoughts. What new circumstances and answers can researchers find because of these incitements? We are at present seeing a total disturbance of the old guidelines in science. The James Webb Telescope is upsetting our view of the universe, and each new picture from this wonder of space exploration is noteworthy. James Webb, the telescope's namesake, would have been glad. Webb was not a researcher but rather came from a business background. He comprehended the meaning of space exploration for humankind as head of NASA during the 1960s. Webb progressed space travel significantly, launching the Apollo program and pushing for space tests. Today, researchers are amazed by the capabilities of the telescope named after this trailblazer. The pictures are so clear and sharp that they take our breath away. For the first time, we have complete examinations of exoplanets some huge number of light-years away. The telescope is uncovering to our scientific community that they have been depending on obsolete discoveries and thoughts for a really long time. At first, numerous researchers are encountering vulnerability and uneasiness as all that they had confidence in may now be refuted. Kaku, a well-known astrophysicist from the USA, is one scientist who is hopeful about these new developments. Kaku has long contended that our past speculations were fragmented. The powerlessness to join the universe of subatomic particles with the universe of shaped matter alone shows that we have not completely perceived essential cycles in the universe. Presently, exoplanets are likewise breaking the laws of physics. It's amazing. At first, just old systems didn't fit into our cosmological models. Then came black holes and massive structures more than 13 billion years old, when the universe was supposedly in its infancy. Presently, even planets challenge our past understanding. The most recent pictures from the James Webb Telescope show exoplanets that challenge our past thoughts regarding planetary data. The telescope reconsidered some of the most peculiar known exoplanets with its sharp eye and interesting cluster of spectrometers. The instruments can separate even the slightest light signals into their singular parts, examining hints of elements, gases, proof of water, and boundaries that uncover the size and orbits of far-off planets. In the process, Webb finds many peculiarities, limits, and the most bizarre planets. One surprising example of these unthinkable worlds that resist the laws of physics is KT9b, an ultra-hot Neptune circling so close to its star that its surface temperatures are sufficiently high to part water atoms into nuclear hydrogen. The extreme proximity to its star leads to a phenomenon scientists call atmospheric blow-off, where the planet's atmosphere is literally blown away from the star. This discovery is unique among all known planetary environments and presents a huge challenge. Webb finds so many exceptions and limits that it's statistically impossible. KT9b is so unusual that it's exceptionally difficult to characterize and represents a specific exception to all the standards we've laid out. We should consider a different universe that scares researchers. WASP-76b, a giant exoplanet with iron raining down from the sky on its night side. The planet orbits its star in a tidally locked circle, resulting in very hot and cool sides. Metals melt and vaporize on the hot day side and harden into iron on the far side, then eventually rain back down to the ground. Researchers are dealing with extreme conditions that vividly illustrate the actual processes on exoplanets and raise more questions than answers. Especially captivating and confusing is the discovery of planets orbiting their stars in the opposite direction to other planets in the same system. Such revelations force astronomers to reconsider hypotheses about the elements of planetary systems and the forces that determine their orbits. WASP-97b is a model of such a world. This exoplanet, found as part of the wide-field search for planets, is a large gas giant resembling our Jupiter, yet it orbits its star in a retrograde course, opposite to the star's rotation. This was considered experimentally impossible according to current theories of planetary formation, which suggest all planets in a system should orbit in the same direction as they formed from the original protoplanetary disk. One hypothesis that explains such orbits is that gravitational perturbations from neighboring passing stars or other massive planets can significantly alter a planet's orbit after its formation. Another possibility is that a gravitational dance between several large planets can push one or more into a retrograde orbit. Interestingly, we don't have to look beyond our solar system to find strange planets. In the Kuiper Belt, we find the dwarf planet 2018 VG18, which surveys have shown to be exceptionally dark and red. Webb spectrometers reveal that this planet is likely rich in complex organic compounds, which researchers call tholins. Despite its significant size and idiosyncrasy, 2018 VG18 remains without an official name because its precise orbit is not determined. Its probable composition, rich in organic substances that are the building blocks of life, and its strange appearance do not match other dwarf planets in the Kuiper Belt. This raises questions. Where does this planet come from? How did it form? And why is it so hard to see due to its perfect distance? Observing 2018 VG18 precisely and over an extended period is very challenging, even with our best telescopes. It is potentially the third largest dwarf planet after Pluto and Eris. Scientists consider it a critical object for understanding fundamental processes in the Kuiper Belt and the formation of the solar system. Planets without a star. Is that possible? Would you believe there are planets without a star? Planets usually form in the debris and gas disks left over from star formation, remaining gravitationally bound to their star. However, rogue planets show that this isn't always the case. These large wanderers drift freely through space without a star. But where do they come from, and how might they survive in the harsh cold of space? Rogue planets can form in various ways. One common method is ejection from their original star system due to dynamic interactions with other planets or close stellar flybys with gravitational forces strong enough to pull the planets out of orbit. Another possibility is that they formed as isolated objects in a star-forming region but without enough mass to initiate nuclear fusion processes like stars. This could also explain the existence of objects called failed stars or brown dwarfs, which are Jupiter mass-like objects that didn't acquire enough mass to start nuclear fusion and become stars. Jupiter, the largest planet in our solar system, was just short of the mass required to start these processes. The James Webb Telescope stunned the scientific community again when it found 80 such rogue Jupiter-mass planets in the Orion cloud. The remarkable aspect of this discovery is the nearly incredible fact that these 80 planets have formed 40 double systems, meaning 40 pairs of rogue planets orbit each other within the densely packed space of the Orion cloud. This is unusual and scientifically intriguing. The sheer number of these planets might be due to the Orion cloud being one of the most intense star-forming regions known. However, more detailed studies showed that these objects are not genuinely planets but somewhere between planets and brown dwarfs in terms of mass. This suggests they are failed stars, as brown dwarfs are among the smallest stars known. Yet, what processes in the Orion cloud are responsible for these failed stars that behave like planets, drifting freely through the universe in parallel systems? This is another boundary challenge for our researchers. These objects might form their own class, pushing the limits of our astronomy. It is possible that such large free-floating objects are much more common in the universe than we previously thought. They might be ordinary but strange to us because we were previously unaware of their existence. We have not been able to identify exoplanets in the depths of space for a very long time, and studying them has always been challenging. The James Webb Telescope represents a milestone in this regard. We are excited by these discoveries, yet researchers are becoming overwhelmed by the new peculiarities and incredible findings. Nothing is as they expected. As science reached an end, the James Webb Telescope was designed to fill gaps in our knowledge and confirm existing theories. Instead of closing gaps, its discoveries are tearing new openings in what we know. As some now say, the crisis web has triggered marks the end of our old science. As Kaku said, we need to rework our course books. But what should we write in them now? No clear new answers have yet been found, and researchers are frantically chasing new explanations. We might need to leave the possibility that our astronomy and cosmology can completely unveil the universe's mysteries. The James Webb Space Telescope, JWST, represents a grand leap forward in our ability to observe the universe. Named after James E. Webb, a former NASA administrator who played a significant role in advancing space exploration during the Apollo era. The telescope is a testament to human ingenuity and curiosity about the universe. Launched in December 2021, JWST is situated at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location offers several benefits for galactic observations, including a stable thermal environment and an unobstructed view of deep space. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet frequencies, JWST is optimized for infrared observations. This capability allows it to peer through vast dust clouds, study the formation of stars and galaxies, and even analyze the atmospheres of distant